if you're watching this at the end of the year, you're going to have seen all these types of probability problems, and this should make sense to you. The big filter is the sample size. Right now, if we're seeing this in the fall, we haven't studied any of this material yet, or even this stuff down here. All we've done so far is look at addition rule, multiplication rule. The word and means intersection. If the sample size is 1, it means multiplication. If the sample size is 2 or more, and we need to know whether we're selecting with or without replacement. We're going to get into conditional probability right now, and we're also going to look at independence. So here's the conditional probability formula. I've seen some pretty good mathematicians mess up on this, and so we've seen this before. It's probability of A given that B has occurred. It's this formula right here. I would like us not to read this as A intersect B. I want us to say it's the probability of A and B happening, because we're going to be able to use this formula whether our sample size is 1 or 2. If it's 1, it's intersection. If it's 2, it's multiplication. If we look at this problem right here, we're going to find the probability of A occurring given that B has occurred. So we're just focused on this Venn diagram. So we're going to select one thing, that's why it's a Venn diagram, and that one thing, we'll know that that thing is in event B, and we want to find the probability that it's in event A. So what we're going to use as we follow the formula is, let's go find the probability something is in A and B. It's the intersection, because it's only one thing selected. That's right there, that's the 0.2. So it's 0.2 divided by the probability that B occurs. B occurs here. Within set B is 2 regions, so that's either the 0.2 or the 0.4, so you add those together, and you get 0.6, that's 1/3, that's our answer. We also learned that we can shrink the sample space. It's easier if we have the Venn diagram to do that than to use this formula, but we'll get the same answer. So here's we'll say, hey, find the probability of A given that B has occurred. Well, knowing that B has occurred, that eliminates this situation and this situation, so the sample space has been shrunk down to 0.6. Out of that 0.6, what's the probability that A has occurred? It's just that 0.2 right there. So you get the same answer, 0.2 divided by 0.6. When you go to this two-way table over here, if we say, let's find the probability of getting a male, given that this person we select has 2 or more AP classes that they have passed. Simplest thing to do, shrink the sample space down. We're given that the one person we selected has this characteristic, so we can eliminate all those results right there. We're just down to these 60 people that have passed 2 or more AP exams. Out of those 60 people, it's 25 of them who are male, so it's easy to see that our probability is 25 out of 60. If we have this situation, it's a little sneakier. If we roll 2 regular 6-sided dice, find the probability that the sum is 8, given that a 3 was rolled. We need a little bit of English going on here. So let's analyze this effectively. If we roll 2 regularly sided dice, then we're going to find the probability, 2 regularly sided dice, we're going to find the probability that the sum is 8, given that a 3 was rolled. So this is how we're going to write it. The sum is 8, that's probably what we're trying to find, but knowing that a 3 was rolled on the 2 dice. So here's what we're going to do. We're going to follow the formula. We're going to say, okay, the probability, we got to first find the probability that the sum is 8 and that that a 3 was rolled. So we go to the table and we say, okay, where are the instances in which the sum was 8 and a 3 was rolled? Well, that would be right here, or that would be right here. So we have 2 situations. So this probability is 2 out of 36, so we got to be careful. If we're going to use this formula, it's out of the entire sample space. In a moment, we're going to shrink the sample space. We get a slightly different approach. So right now it's 2 out of 36. Now divide that by the probability of rolling a 3. We roll a 3, let's use this color right here, in any of these 6 situations here, or in any of these 6 situations here, but that one got counted twice. So there's really 11 distinct situations in which a 3 was rolled, so that is 11 out of 36. If we do good math, multiply with the inverse or whatever, we're going to end up with 2 11ths as our final total. Now, the simplest thing to do if we do have the lattice diagram, which we probably need, we're going through this bad boy anyway, is just to say, okay, let's shrink the sample space. If we know, if it was given that a 3 was rolled, then the sample space goes from 36 things down to just those 11 things that involve a 3 being rolled. And out of those 11 things, there's only 2 in which you get a sum of 8. So it's always easier to shrink the sample space if you can see the whole sample space to begin with, either by a lattice diagram or by a two-way table or by a Venn diagram. Then we get to the mother of all conditional probability problems, the disease problems. Here we go. Suppose 3% of people living along a certain canal have the lobes of their ears falling off. Wow. So it's like the ear canal. It says, yeah, the lobes are falling off. The lobes, the ear is falling off. But there's this dude that's really artistic. He gets the lobes, he repaints them all beautifully, and he gives them back to them. And he drives this van around town, picking up the lobes and giving them back. It's really amazing. They call the guy Julius Caesar because he's always saying, lend me your ears. And then when he goes by, they say, hey, look at that van go. Okay, so it's ears. Yeah, we got a blood test that can be given to detect the condition. It gives a positive result for 98% of the people with the disease, and then it gives a positive result 4% of the time when people don't have the disease. Keep in mind then, you're given two different probabilities of testing positive. That's going to help us to set up the problem. Now, if we randomly select a person who tested positive, find the probability that he or she does not have the disease. Okay, here's what we do. Again, good English, we're going to say if we randomly select a person who tests positive, that is an introductory dependent clause. Ignore it for just a moment. If we go past that thing, the main sentence here, the main body of the sentence is asking us to find the probability that a person does not have the disease. So the way we're going to write this down is we're going to find the probability that the person does not have the disease, because that's ultimately what we're being asked to find. Now we consider the introductory dependent clause that says if the person we selected tested positive. So that's given that the person tested positive. So there's our situation. Find the probability that don't have the disease, but given that they tested positive. Okay, so we go right here. We can think about all these this information that we have. There's the formula ready to go. Now what I'm going to suggest, the best way in my opinion of years of teaching this for most kids to be able to get these problems right consistently is to go with a tree diagram. Remember, a tree diagram is used when you select two or more things. So we're going to consider the blood test to be one event, and then whether or not they have the disease to be another event. It seems to me that this is the best way for us to consistently get the answers right, and that's why I want us to read that as and not always intersection. And will now mean multiplication because we're going to be selecting two things. So here we go. We're going to build a tree diagram. We have to decide, do we put testing positive and negative first, and then whether they have the disease, or the other way around. And here's where, because there's two different probabilities for testing positive, that we realize the first branch of the tree has got to be disease and not disease. We can't put positive and negative because there'll only be one place for testing positive. This is how the tree diagram has to be formed, that in essence we have to realize if they have the disease, then their testing positive has a 98% chance of happening, and them testing negative then has a 2% chance of happening. That is for the 3% of the population who have the disease. Now then, theoretically, for the other 97% of the population, their likelihood of testing positive or negative is based on this. There's only a 4% of them that are going to test positive. That's what we call a false positive. And by default, 96% of them are going to test negative. So here we go. We've got to find this probability. So we use the formula. Find the probability the person does not have the disease and they test positive. That's right here. Does not have the disease and they test positive. We multiply those two probabilities together. We get 0.0388. Okay, now that goes in the numerator, 0.0388. Divide that by the probability that they test positive. Rephrase using and or. How will they test positive? They can test positive by not having the disease and testing positive. That was the 0.0388. Or means addition, they could have the disease and test positive. If we multiply those together, we get 0.0294. So there is our result. There's our conditional probability. This puppy divided by this puppy, it gives us, as our final answer, 0.5689. That's roughly 57%. That's good to know. Even if a person tests positive, only 57% of the time, 57% of the time they don't have the disease. That means only 43% of the people who test positive actually have the disease. So there's false positives, false negatives. We'd rather have a false positive in real life than a false negative. So that's the way we do the problem. And lastly, you could do this shrinking the sample space once you set up the tree diagram. And really, it's in essence the same thing we just got done doing in the formula. Given that the person tested positive, well, that only happens here or here. So we've just shrunk the sample space down to the sum of those two things. And the probability then that out of that shrunken sample space, the person did not test positive is the 0.0388 divided by the sum of those two things. This, divided by the sum of those two things, gives it the same answer, it just shows a little bit more understanding. So, that's the beginnings of conditional probability. Later on in the course, in the next couple days actually, when we get to problems that are really, really difficult and they make you think, odds are it's some sort of a conditional probability problem.